Okay, did my voice come through? Right. You can hear me?
I can hear you.
Yes. Now in this presentation, I will introduce you image steganography techniques with their design challenges and how perform well in certain areas. Uh, so my voice comes well. Okay. In image, let's start with what is steganography. Steganography is a concept of hiding secret information in a stego object in order to avoid detection. Uh, it first used in ancient Greek, uh, which it also means covered writing in Greek. Covered writing in Greek. So the first examples are in Greece, the, where the where they hide message uh, in messengers shaped head in order to avoid detection. And also in World War II, Germany, they used microwave technology to sharing photographs of manuscripts or blueprints to hide, hide them. Uh, we can we can model the steganography scheme into a prisoner's problem, where there are two prisoners imprisoned in different cells and a warden which observes the whole communication between these cells. Uh, let's think about that. These two prisoners is planning an escape plan. And in order to execute the plan, they have to communicate without drawing attention of the warden. If warden sees any suspicious move, they can take an action. This is the general flow of the prisoner's problem, where one of the prisoners used to hide their information with a cover message by using secret key, but it's not necessary. By use proper steganography algorithm, uh, the warden sees the message. If sees any suspicious move, uh, they can take an action. But if not suspicious, they can let go the message. And then the destination, it used extracting algorithm to extract the hidden message in Stego object. In this prisoner problem, we have two different warden modes, where active and passive. In passive case, which is more highly to encounter, uh, the warden only takes a general look on the message. It's like just only sees the message and lets go the message. And in active warden case, they can alter the message in different ways. They can even uh, perform some statistical tests on messages, the objects, to understand if there's any suspicious move going on. But there are but it is less likely to encounter like that. Today I will introduce you image steganography, where they will use image files to hide these messages. Uh, the terminology of this image steganography is we use cover image to hide the message. we name the secret message as payload. Payload, and when payload hide hidden in cover image, it's produced the stego image. So you can say why we didn't use encryption instead of steganography. I mentioned that because in encryption, when warden sees the encrypted message, they see random stream of the random characters. So it will create the suspicion. So we will not want to detect, create a suspicious move. So that's why we hide the important information into a not suspicious thing, object. So we have some performance measures for 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 a good image steganography technique. These are creates the design challenges, which are these five: imperceptibility, robustness, payload capacity, security against steganolysis, and complexity. To explain them, imperceptibility is visually undetectability of the change made on file, which is highly useful on passive warden case. In order to perform well in this area, visual quality has to be maintained. And in some cases, in some techniques, cover selection also plays a big role. In order to maintain robustness, steganography algorithm has to be hide message in a way to not damage it until it reaches its destination. So, like these attacks can be like image processing techniques. They can alter the message, damage message, or instantly remove message by cropping or compressing. Payload capacity also is a big, it's an important design challenge, because you don't want to see, you don't want to warden see that some unrelated image sequence that also create the suspicion. So in some cases, payload capacity also is a concern. And security against steganolysis. Steganolysis is the countermeasure for steganography, which consists of some statistical tests to understand if there is alterations made on image file. And complexity is also a concern in nowadays, because since there are more complex algorithms are produced, the computational power also, computation cost is also increases. So that makes it's some techniques are look good on paper, but they are very narrow usage area, and it's highly unpractical. Okay, we can explain image steganography techniques in 4 different categories, where we can hide payload by altering the image pixels directly, or transform domain, where we can hide the message into transform coefficients, which are used to compress image files, and spread spectrum techniques, which is hidden as white noise, and model-based techniques, which are used for counter the specific steganolizer methods like random, like some approach like detects randomness or else. Now, spatial domain techniques are the most basic approaches, which are used in earlier days. Also, they are still used mostly nowadays because they are simple to employ and useful in passive boredom cases, which are highly likely to encounter. First of them is the LSB's substitution method, the bit substitution method, and these are the common basic steganography techniques which use only the least significant of the RGB values to hide the payload, like altering the RGB values. This selection of pixels can be done in various ways, like random selection or selecting into various places of the images, but that sometimes requires a key and makes it not practical in some cases. The second, the pixel value difference, where we hide the message into differences of adjacent pixels. The main idea stems from differences can be noticed in smooth areas and edge areas. Like in smooth area, you can be detected easily by human eye, but in edge areas, there are more pixel value difference between adjacent pixels. In order to do that, the payload data, like these, hidden in the pixel value differences between the adjacent pixels. Like they use gray value, like in this example, these two adjacent cells are have a difference of 15, but in this new difference, the 18 and these two pixel values are all modified according to them. In pixel value prediction method, in these two previous technique, they modify the pixel values directly, which can create the distortions very noticeable way. In order to prevent this, they use pixel value prediction to employ a predictor, and modifications are based on the prediction error values produced by this predictor. And modifications are recorded on key, and also pixel values are modified according to this modified prediction error values. So it will decrease the statistical changes on image. In fourth technique, we use multiple base notation system. Let's reconsider the least significant bit, which represents the payload into binary system. In this technique, it will change into some user-adjusted modular system, like for example 5, which can hide the more data, like 2.5, range of 2.5. This will also create more distortions in the picture, so it can be highly likely to noticeable. by any observer. In constellation index modulation, it is very different technique aside from, but it's still used on, it still modifies the pixels directly. Now, in order to do that, payload bits are modulated, sequence of bits is modulated with payload bits, and cover image quantized by these quantizers with user-defined quantization step to spread over the payload, spread the payload data over the image at certain rate. This will result in high security, but also it suffers from low payload capacity as well. So you can see that these techniques are directly change the pixel data, which can only be usable at lossless image types like PNG, bitmap, or GIF. So in simple image compression technique, the all data hidden will be highly likely to lost. So in order to prevent that, there are transform domain techniques produced, which are based from image compression processing. Firstly, it will be easier to understand image compression before diving into these methods. First, the source image are divided into 8 to 8 blocks in order to represent them by coefficient. And when the compression processing, it uses some transformation, mathematical transformation function like discrete cosine transform, discrete Rayleigh transform, or discrete Fourier transform, or like those. And after that operation, it quantizes the coefficients in order to discrete the values produced. And it will encode the quantized coefficient by some encoder in order to get the compressed image. Now, it can be seen that these two are the loss stages. You can see that there is data loss in quantizer because data is altered in this operation. But in encoder, it won't be changed. It just encodes the data. So it will be suitable that the encode hide the payload into this section. Like in discrete cosine transform, we use this quantized discrete cosine transform coefficients to hide the payload into image cover image. It can be performed in various ways, which I will introduce only two of them, which is F5 and outphase. In F5 technique, it is permits the DCT coefficient in order to spread the change made on coefficient evenly over the entire image. So the statistical properties are maintained, and then does a custom matrix embedding in order to minimize the amount of modifications to provide inverse stability. In outphase methods, it hides the payload into pseudo-randomly selected coefficients generated by a key, skipping the coefficient values ones and zeros because they will be significant. So, in order to provide visual quality, this cannot be modified directly, and does correction on these skipped coefficients. In discrete Taylor transform-based techniques, the general flow of the compression operation is like that. Uh, in this flow, there are two loss stages, which are tier 1 encoder and quantization. And there is also four main hiding points, which are after forward, BWT, which provides higher capacity because in this section there are four main subbands to hide the data, hide the payload, because there are four main subbands, so it will provide high capacity, but the the technique has to be robust enough to survive out of these two loss stages. It can be after quantization as well, but it still needs robust as well because it has to be survived in this section. Also, it trades off the capacity with higher security. It can be also tier 1 corrections after tier 1 encoder. It will also has lower capacity than after quantization, but it provides higher security and robustness because there is one more encoding operation as well. It can be tier 2 corrections. This will provide low complexity, but visual quality will severely suffer the changes made in tier 2 corrections. So in the third category, we have spread spectrum. In these general techniques, most of them use some parts of the image to hide data, but it will make suspicion. It will create suspicion because you can see the image and some parts are distorted and some parts are not. So spread spectrum, so they generate proposed spread spectrum in order to spread all differences by using the white noise. So you can see the differences without seeing the actual cover image. This is the general flow of the spread spectrum encoding. You can first encrypt the payload by key 1. After the low rate error control coding, there is pseudorandom noise generator seeded by key 2 to generate the noise, white noise. And after the modulation, key 3 is used for EXO, for embed, it's for hide the message, hide the payload. And when it's used with XOR with key, because changes have to be insignificant to inspect by human eye. And after the quantization, the Steganography image is generated. Now, when you look at it, it will generally perform well in all areas, but it is so much complex to actually employ in every time. So it's looks good on paper, but it's highly unpractical and very narrow area to use actually. There's also decoding, and decoding is as well is very complex operation. In model-based techniques, the main aim is the maintaining the statistical integrity of the coverage by modeling the statistical properties. These techniques are, as mentioned, are used to counter the specific signalized techniques. So there are much more proposals made on this area, but cannot be easy to cover at such a limited time, so I will only introduce the three of them. One of these uses conditional probability model in order to model the statistical properties, which is used on a JPEG cover image represented by a random variable x, and image divided into two parts, which is significant and insignificant. Modification in insignificant parts are not easily detectable by human eye, so payload hidden into these insignificant parts, and insignificant parts are modeled by conditional probability of this notation. So the changes are also sent to the destination with a key. And when in the receiver side, payload can be extracted by entropy encoder. It's actually encoder and decoder used to check hiding process with the probability distribution of modified insignificant part. In this second approach, it is based on this substitution. It's basically the main aim is to regain the smoothness of the image. So in order to provide that, it used basically clustering the neighboring pixels. Clustering method is defined by user-defined threshold, performed by user-defined threshold value, which affects the cluster size. Cluster size, the higher cluster size provides more capacity, but also it makes visual distortions because when you see the image with a higher cluster, you see there are some blurry pixels, blurry areas in the image, so it will not practical to use very high threshold value. And the third approach, which is also named data masking, the main idea is to counter the Steganography techniques that can detect the randomness. So, in order to decrease the effects of the randomness, the payload data first preprocessed by a white noise filter to reduce the effect of randomness, because when the payload data is represented by in binary array, it is actually in representation on the image, it will be just white noise. It doesn't make sense. So in order to decrease this randomness, it has to be used white noise filter, which is proposed as well. In order to summarize this, techniques, you can see that every technique has their own upsides and downsides. So there are not ultimately best technique. So which can be summarized that this is the evaluation table of the introduced methods. We can see how they are well in produced performance measures. In this, you can see that the spatial domain techniques are well in capacity, but highly suffers in other performance measures. But since they are low on complexity, they are highly used in practical. Also, transform domain techniques, which are used for compressed image files, they also provides high in other techniques by trade-off the capacity. You can say that the spatial domain techniques and transform domain techniques are well the passive boarding case, because they will only take a general look so they can notice a difference. But active boarding cases, we need high security, but you will nearly less likely to encounter them. So they are highly unpractical, and also complexity, the cost makes them highly unpractical, but they are sometimes useful in those cases, which are actually the spread spectrum technique is nearly well on every area, but it has so narrow usage. So that's the summarizes the image steganography techniques that the main basic ideas, the fundamentals. So that's all.
Okay. Is there any questions? From the students who are in attendance? Anything that anybody didn't understand? Okay. All right. Well, Barak, what was the most interesting part to you? That what was something that you learned from this that was the most interesting part to you that you had not known before? Oh, actually, it looks like there may be a question. Bodesh, feel free to answer Betula's question first, and then I wanted to know what was the most like kind of profound thing to you, the thing that you learned the most.
Okay. The advantages between cryptography, the security of the steganography is behind. Comes from the hiding the message. It creates less suspicion. But cryptography is just converts the message into some random sequence of characters. So when you see an encrypted message, you will see some things hidden. But when you see a stego object, you doesn't suspect anything. You don't understand anything. So that will be create the security behind the steganography.
Okay. Does anyone else have any other comments or questions or?
Like secret communication. Yeah. There are not so much areas, but some also there are some interesting areas that can be used. Like there's a modeling program which uses steganography where it used the photograph of the created character model, and it used to save its properties into the picture of the model by using steganography like that. There are some interesting areas like that.
All right. Well, we'll go ahead and end there if there are no other questions. One thing to remind those of you who are here live and those of you who are watching this video later, I will try to make so you have comments on this presentation in some form as part of an assignment. Depending on how the grading does it, it may end up being just a portion of your final exam or something like that. Because the last day of class is a week from today, and so I don't think, and I think I have to have all grades in by that day, so I don't think I will be able to make it an assignment due that day. But I'll try to figure out a way to make sure that you guys give valuable input and valuable feedback on these presentations to our students, to our graduate students who have worked so hard on this stuff. Okay. All right. So other than that, we'll call it a day for today. Have a good lunch, have a good weekend, and hopefully these lockdowns will end eventually. And we will see you guys a week from today. Oh, so sorry, Nita. Go ahead.
It is just a shape modeling of the steganography. Like there's two nodes which tries to communicate without taking so much attention. So they are trying to avoid the warden like that when they are trying to execute the escape plan. That's the connection. So they want to communicate beyond the warden's awareness.
All right. Thank you guys. Thank you for that question, Nita. And thank you again, Barish, for the informative presentation. I remember taking a class that involved that when I was in graduate school, and so it was very interesting to be reminded of some of that. All right. So thank you guys for attending again, and last chance for anybody to say last minute questions or comments. All right. Well, other than that, I'll see you guys next week. Have a good weekend.